Hello everyone, my name is Noshin Huma Ahmed and I am presenting with my teammates Miftilul Mehboob and Shomo Dipto Dash. We are students from the Department of Computer Science and Engineering at BRAC University, Dhaka, Bangladesh. Our project is titled Real-Time American Sign Language Recognition using a CNN LSTM hybrid pipeline with MediaPipe landmark features. In short, we built a working system that recognizes ASL alphabet letters through a standard webcam in real time. Over the next 10 minutes, we will walk you through the problem, the system, the results, and what we learned. The World Health Organization reports that over 466 million people globally live with disabling hearing loss. Sign language is their primary mode of communication, yet most hearing people cannot understand it. This creates a real barrier in hospitals, schools, and daily life. Our goal was simple: build a low cost ASL recognizer that runs on a normal laptop webcam with no special hardware. This is harder than it sounds. 3 challenges shaped our design. First, visual similarity. Letters like E, S, M, and N look nearly identical and differ only in small finger positions. Second, motion dependency. Letters Z, J, and Z are defined by hand movement, not a single shape. Third, speed. A system is only useful if it runs fast enough for real conversation. These 3 constraints, similarity, motion, and latency, drove every architectural decision we made. We trained on the ASL alphabet dataset from Kaggle, 87,000 images across 29 classes. Letters A through Z plus delete, space, and nothing. Every class has exactly 3,000 images. Making the dataset perfectly balanced, we split it 80 by 10 by 10, 69,600 for training, 8,700 for validation, 8,700 for testing, with zero overlap verified programmatically. Images were resized to 160 by 160 pixels and normalized to the range 0 to 1. During training, we applied 4 augmentations: brightness, contrast, saturation, and random cropping. One important decision we deliberately excluded: horizontal flipping, because mirroring an ASL sign can produce a completely different or invalid gesture that would corrupt our labels. Our pipeline has 5 stages. First, the webcam frame is captured, flipped for a mirror effect, and color converted about 5 milliseconds. Second, MediaPipe detects the hand extracts 21 joint landmarks, 16 milliseconds. Third, a fast geometric landmark classifier analyzes those landmarks and predicts the letter, just 0.21 milliseconds. Fourth, every third frame, a full CNN classifier also runs on the raw image, 62 milliseconds. Fifth, both outputs are fused through a 7-frame majority vote, and the sign is only committed to the output when confidence stays above 95% for 1.5 seconds. If no hand is detected at all, the system immediately clears the prediction buffer, preventing false letters from accumulating. Key takeaway: 20.2 FPS overall, up to 60 FPS in landmark only mode with a sub-millisecond geometric fallback. I will now hand over to Miftilul. Thank you.
Thank you. Our CNN is a custom 5-block architecture. No pretend weights. Each block follows the same pattern: convolution, batch normalization, ReLU, max pooling. The filter count doubles each block: 32, 64, 128, 256, 512. This progressive increase lets the network learn increasingly complex hand shapes. After the 5th block, global average pooling collapses everything into a single vector, fed into a 256 neuron dense layer with 50% dropout, then a 29 class softmax output. Total model size is about 650 kilobytes. The landmark classifier works completely differently. It is no neural network at all. It takes the 21 media pipe landmarks, then normalizes them relative to the wrist, then checks whether each finger is extended or curled using a single distance ratio. If the ratio is above 1.05, it is extended. Below 0.85, curled. Those 5-finger states got matched to ASL letters using handcrafted rules. The results: 0.21 milliseconds per frame, over 300 times faster than the CNN. It confidently handles about 18 letters. The CNN covers the ambiguous rests. We chose CNN LSTM over 3D CNN because 3D CNNs require 200 to 500 milliseconds per prediction, simply incompatible with real-time use. Training ran in two phases. Phase 1 used a learning rate of 0.001 up to 20 epochs. Each stopping kicked in if the validation loss didn't improve for 5 consecutive epochs, and the learning rate automatically halved when progress stalled. This phase builds strong initial weights quickly. Phase 2 loaded the best checkpoints from phase 1 and then continued with a lower learning rate 0.0005 with patience extended to 7 for finer, slower refinement. Uh, looking at the uh, Looking at the training curves, the validation loss tracks closely with the training loss throughout. No sharp divergence, and that tells us dropout. Batch normalization and augmentation did their job. Then the model generalized, not just memorized. These screenshots are from our own live webcam testing. The real system, not this is a real system, not a simulation. On the left, the system recognizes the letter G at 90% confidence and 48 frames per second. The CNN is not running here at all. The landmark classifier alone is handling it at 0.21 milliseconds. You can see the uh, red landmarks on the hand and the green bounding box around it. On the right, the letter F is at 96% confidence. Notice at the top left it says CNN. Dell 37%. The CNN disagreed and they predicted Dell, but with the very low confidence. But it is very low confidence. The landmark classifiers F wins here. This is exactly the kind of disagreement our fusion system is designed to handle. This confirms the system work. The system works in a real room, you under real lighting with a real person's hand. Our test set was a our test set was 8,700 images. The data model had never seen during the training. The standalone CNN achieved 81.77% accuracy with the full CNN LSTM temporal pipeline. 93.47%. That is an 11.7 percentage point improvement purely from the temporal architecture, the fusion, the voting, and the confidence hold. Most classes score above 0.85 in precision, recall, and F1. F achieves near perfect precision, but some classes clearly struggle. E confuses with E confuses with A, S, and B because all are closed hand shapes. N and M confuse each other for the same reason. W and V have reduced precision because multiple upright fingers can trigger both. Um, these are not random errors. They reflect genuine structural similarity in the gestures themselves, uh, and they tell us exactly where to focus next. I will now hand over to Shomo for the next slide.
Thank you, Miftul. The confusion matrix diagonal correct predictions is strong for the vast majority of classes. Notably, the nothing class scores 300 out of 300. Every time there was no sign in frame, the system correctly predicted nothing. This is critical for real-world use. The system will not generate phantom letters where the user is resting or transitioning between signs. Del and space are similarly reliable. The main error cluster E confuses with A, B, and S. N confuses with M. U and V are mutually confused. All of those share nearly identical finger configurations. They differ only in thumb position or finger spread, which can be lost at 160 by 160 resolution. Understanding exactly where the model fails is as important as knowing it achieves 93%. We benchmark every pipeline stage over 500 consecutive live frames using high precision timers. Frame capture and color conversion 4.85 milliseconds. Media pipe hand detection 15.87 milliseconds, the second largest cost. Running every frame. Landmark classifier 0.21 millisecond, effectively free. CNN interface 61.74 milliseconds. The primary bottleneck, accounting for 74% of frame cost when hand is active. Total average 49.45 milliseconds per frame, about 20.2 FPS. Without a hand in frame, the system reached 60 frames per second. With the CNN running, it drops about to 12 frames per second for those frames. Running the CNN only every third frame yields the 20.2 frames per second on average. Compared to prior work, VGG16 achieves 95% accuracy, but only at 8 frames per second. ResNet 50 reaches 97.8 98% at 12 frames per second. Efficiency net B0 reaches 98.9 at 15 frames per second. We are 4 to 5% below points below the top accuracy models, but we are the only system in this comparison with confirmed real-time throughput and sub-millisecond landmark fallback. We want to be honest about our limitations. First, our 93.47% was measured on test images from the same dataset we trained on, a controlled setting. Real-world accuracy across varied lighting, cameras, and signers will likely be lower. Second, J and Z are defined by motion paths, not static poses. Our temporal layer smooths predictions but does not model trajectories. These layers remain weak. Third, at 160 by 160 pixel, fine finger details can be lost, directly causing E and MS confusion pairs. Fourth, the CNN at 62 millisecond per call is too slow for low power devices as is. So, for future work, our top priorities are TensorFlow Lite INT8 quantization to reduce CNN latency to 10 to 15 milliseconds. Training with more diverse real-world data to close the dataset gap, adding proper bidirectional LSTM for J and Z, and eventually extending the system towards continuous sentence-level ASL understanding, the true practical goal. So let me bring everything together. We build a hybrid real-time ASL recognizing system combining a 0.21 millisecond geometric landmark classifier with a deep CNN fused through 7-frame majority voting. Our 4 key contributions. First, the dual pathway architecture itself, speed and robustness from a single combined system. Second, 93.47% test accuracy, 12% point improvement over the single frame CNN baseline. Third, confirmed real-time performance at 20.2 frames per second, backed by par stage benchmark over 500 live frames. Fourth, explicit null frame handling, so the system behaves cleanly between signs. This is a research demonstration, not a fine finished product, but the architecture is a solid foundation for work ahead. We thank the Kaggle ASL data creator and Google Media Pipe team and the TensorFlow and Keras community. So thank you very much for watching.